All right, here we are, sequence and series, day number 2. We're going to do some sequence evaluations, so let's get into it. All right, so a sequence is a list of numbers, as you know, called terms in a definite order. We write them in this form, A1, A2, A3, as an, where a sub n is the nth term of the sequence. The sequence is infinite if it contains an infinite number of terms. It's finite if it contains a finite number of terms. So an example of this would be where a sub n equals n over n plus 1. And this would denote the infinite series of discrete values in this order. And we can plot a sub n given like this. Now you might ask yourself, well, what's the difference between that and say f of x equals x over x plus 1? Well, there's actually not a whole lot of difference there. The only difference is that our function x over x plus 1, right, will be continuous approaching this value of y equals 1, where this sequence is not continuous. So we're going to be using some of our skills of limits today, as well as the squeeze theorem. So let's get to it. All right, so this slide right here basically just allows us to write a sequence as a function. So consider a sequence a sub n, which can be expressed as a real valued function. Write a sub n as f of n, where n is all numbers in z plus, for f a real valued function. The behavior of f of x as x goes to infinity could also describe a sub n as n goes to infinity. A couple of properties here. You'll see in number 1, if we took and called this sequence f of x and found that the limit equaled L, then the limit of the sequence would also equal L. And in the second piece, if the limit as n goes to infinity of a sub n equals L exists, and g is any function continuous at x equals L, then we can use this idea of a constant, pulling it out in front and evaluating the limit without the constant. Or excuse me, this is a composition. So if we had g of some sequence, then we could, as long as it's continuous at that point L, we could take that out, evaluate the limit, and then plug that value that the limit evaluates to into g. So let's do some work here. Consider this function x over x plus 1. This is just properties of limits, you guys. Okay, so if I took the limit as x goes to infinity of x over x plus 1, one method that we have used before is to multiply everything top and bottom by 1 over the largest degreed term in the denominator. Right? So I would do this, multiply top and bottom by 1 over x. Well, in the numerator, what would that give me? Well, that'd give me x over x, which is 1. And in the denominator, I'd get x over x, which is 1, plus 1 over x. So the limit as x goes to infinity of this would be 1 over 1 plus 0, which would equal 1. Another way you could look at this, and we've done this in simpler terms, was to take the highest power on the top, highest power on the bottom, and divide their coefficients, right? And we kind of negate this because it's not going to make a difference as x goes to infinity. So there you'd also get a limit of 1. So let's read the rest of this. By considering n sufficiently large, the terms of the sequence, I'm right here, will be as close as we like to the value 1. We say that the limit then equals 1, and we can apply that then to the sequence, even though we've talked about it as a function. If the sequence is convergent, then its limit is unique. So if you read up here, if the limit of the sequence exists, then we say it converges. Otherwise, that sequence is divergent. We don't know what it is. Nothing new there, you guys. We're just looking for the limit of a sequence in terms, or written in terms of a function. All right, so limit theorems for sequences. I want to highlight just one specific thing here. Last chapter we talked about convergent integrals, improper integrals. Okay, this is for sequences only. Basically, if I took the limit as n goes to infinity of 1 over n, we'd get 0, which means it's a convergent sequence. Okay, that sequence would eventually get close enough to 0. This is always going to be true in this form as long as p is greater than 0. Okay, so that's different than back when we did integrals, right, from 1 to infinity over 1 over x dx. This was only convergent if p was greater than 1. Now when we talk about sequences, p just has to be greater than 0. Alright, let's use that and go from here. Alright, a couple more things. Comparison tests for sequences, just like comparison tests for integrals. Same properties, pretty much, same everything. If a sub n diverges, then it will force b sub n to diverge as well. If b sub n converges, it will force a sub n to converge. This is basically the squeeze theorem for sequences. So suppose a sub n converges, right? This is just a property of addition, property of multiplication, and property of division. I'm not going to go over those right now. Alright, so let's say we want to know the limit as n goes to infinity of the following thing. Right? Okay, so I want the limit as n goes to infinity of this thing. Well, what I'm going to do is I'm going to divide everything in top and bottom by the largest powered term in the denominator. So that will be n squared. Right, that's where it originates. N squared, n squared, n squared. Okay, so let's see what we get. Limit as n goes to infinity. You're probably looking at the bottom right there, looking at the 4 natural log of n and going, what the heck? And you're right, it's fine, we'll get there. I'd get 2, right, reducing there. I'd get plus 4 over n. I'd get minus 3 over n squared. I'd get 1 in the denominator minus this thing, this question mark, right? Because as n goes to infinity, that's for sure going to 0. That's going to 0. So I want to say I'm going to get 2, but I'm not sure. So what I got to do is I got to analyze this 4 natural log of n over n squared. Alright, so let's look at that. So what would the limit as n goes to infinity of 4 natural log of n over n squared be? I don't know. But what I do know is that 4 natural log of n will always be less than 4n. Alright? And those will both always be greater than 0 as long as n is greater than 1. So if I divided everything by n squared, divide by n squared, okay, I would get 0 is less than 4 natural log of n over n squared, which is less than 4 over n. Alright, so then if I took the limit of all of these things as n goes to infinity of each of those things, the limit as n goes to infinity of 0 would be 0. I don't know what this is going to be, but I do know that the limit as n goes to infinity of 4 over n, if this power, p, is greater than 0, it's going to go to 0. And it is, it's 1. That's going to be 0. So this has to be 0. It's got to be between 0 and 0. So it's got to be 0. Therefore, the limit as n goes to infinity by the squeeze theorem of 4 natural log of n over n squared is going to be 0. So I can go back up here. I know that this thing is going to go to 0. Therefore, I'm going to get 2. Right on, using the squeeze theorem. Alright, squeeze theorem for sequences. Right here, you can kind of check that out. And I'm going to move on to another example. Alright, so sine of n over n. Okay, so the limit as n goes to infinity of sine of n over n. No idea, right? I know what the limit is as n goes to 0. That's 1. It's a special limit. But what about this? What if I took sine of n, use a little squeeze theorem work here. Isn't that true? So then wouldn't this be true? So if I took the limits as n goes to infinity of each of these items, then the limit of sine of n over n as n goes to infinity should be between the limit here, which is 0, and here, which is 0. And therefore, by the squeeze theorem, yet again, if I knew that this limit had to be greater than or equal to 0 or less than or equal to 0, that dang thing better be equal to 0 by the squeeze theorem. Squeeze theorem. Boom. Alright, let's look at the assignment for a moment. Alright, so let's look at A. Clearly the limit as n goes to infinity of this thing. Degree on top is larger than degree on the bottom, therefore that would be 0. This limit is pretty interesting, but I would just use properties of logarithms. This would actually be 1 plus n over n, natural log of 1 plus n over n. I just use the division property of logarithms. So if I took the limit as n goes to infinity of that, okay, as n goes to infinity, this inside piece would just go to 1. So what would be happening is this would be approaching the natural log of 1, which is equal to 0. Alright, so that limit would be 0, both of those first two. This limit, if you can probably clearly see it now, highest power, the limit as n goes to infinity of a sub n would equal 3/5. This one here is kind of a mess, but you got to get a common denominator. So I would multiply top and bottom here by n plus 1. You can do this on your own time. And here n squared plus 1. This actually converges. So don't be fooled into thinking because the degree here and the degree here or the degree on top is bigger that's going to diverge. Same thing here. Degree 1, degree 2. It actually converges, I think, to 1. Okay, let's see here. Let's do, boy oh boy. How about a quick one here in F? Right? If I were to take this to the 4th power, it's going to get a massive expansion of this binomial. But the highest powered term would be 2 to the 4th n to the 4th. And the highest power on the bottom, the leading term would be, what would that be? 81 n to the 4th. So what is 2 to the 4th? 16, I think. Yeah, I think it's 16. So I'd be getting this. And if I take the limit as n goes to infinity of that polynomial expansion, I'm just going to get 16 over 81. So it'd be convergent. All right, how about A on number 2? Let's look at that one. All right, so I want to write out n factorial. So let me write out limit as n goes to infinity of, I'm going to write out n factorial as n times n minus 1 times n minus 2 times n minus 3, dot, 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 all the way down the line. And here I'd have n plus 3, n plus 2, n plus 1, n minus 1, etc. What we're going to get here is we're going to get some cancellation. These terms will start to cancel, and they'll cancel the rest of the way down, okay, until there's nothing left. So it'd really be like taking the limit as n goes to infinity of 1 over, looks like n cubed plus a bunch of garbage, right? N times n times n. which of course, in this case, degree on bottom is bigger, so that would be 0. So that would be convergent as well. All right, let's see here. Let's pause for a second. Let's start with a quick one here. I'm going to use the squeeze theorem on this one. I believe that cosine squared n would be less than or equal to, over 2 to the n would be less than or equal to 1 over 2 to the n. And if I'm squaring cosine, that would bring all my values positive, so that'd be greater than or equal to 0. Since the limit as n goes to infinity of 1 over 2 to the n would equal 0, then I know that the limit as n goes to infinity of cosine squared n over 2 to the n would have to also equal 0. Cool, cool. Let's look at this last one here and we'll call it a day. Find the limit as n goes to infinity of the following. I got 1 over n squared plus 2 over n squared plus 3 over n squared all the way up to n over n squared. So you use the arithmetic sum equation. Well, what is that actually asking us to do? First, I'm going to do this. I'm going to write this in a compacted form. I'm going to go 1 plus 2 plus 3 plus 4 dot 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 plus n all over n squared. Alright, so let's then use the arithmetic sum sequence, or the sum equation here, because that's just an arithmetic sum. What is that exactly? Well, that's n over 2 times n plus 1. Right? First term, let's see if you remember this. N over 2, first term plus nth term. Well, the nth term is n, the first term is 1, and so that's where that comes from. Okay, so now let's do a little bit of work here. This would be over n squared. Okay, so let's expand the limit as n goes to infinity. This would be 1/2 times n squared plus n over n squared. Right? All I did was distribute and pull out that 1/2. Therefore, I really could just pull that 1/2 out in front here and take the limit of this. Well, the limit of that would be 1, right? Coefficients. Therefore, this would be 1/2 times 1, which should equal 1/2. Therefore, we have a convergent sequence. All right, I think that's it for today. That is day number 2 on convergent and divergent sequences using limits.